We have calculated p-value of slope, confidence interval of slope, and R-square in the previous video using summary method of stats models. Are they valid claims? In other words, do those assumptions which are necessary for inference hold true? In this video, we will discuss how to diagnose models and validate assumptions of models. To validate four assumptions about a population, we only need to demonstrate that our sample data is not against these assumptions. Validation of linearity is straightforward through scatter plot of y and x. In our case, scatter plot between median price and number of rooms has linear pattern. For independence, we just need to demonstrate the observed error is independent mutually. Alternatively speaking, there is no series correlation in errors. First, we can plot residual plot, which is the plot observed error. There is no obvious pattern in this plot. For quantitative validation of independence, we need a Durbin-Watson test. The norm of Durbin-Watson is that there is no series correlation in errors. In the output of summary, we can get a Durbin-Watson statistics d equal to 0.684. To find a critical value, it is really cumbersome, which depends on sample size and the number of predictors. We have a rule of thumb that test statistic values in the range of 1.5 and 2.5 are relatively normal. If below 1.5, error may be positively correlated. If above 2.5, it may be negatively correlated. Hence, the assumption of independence is violated. For normality validation, we can use quantile-to-quantile plot or QQ plot. We use method proplot from Python package scipy.stats to draw QQ plot. The first input of proplot is the standardized error. The second term dist equal to norm is to compare the distribution of your standardized error with normal distribution. If errors follow normal distribution, they will fall on the 45-degree line roughly. In our model, it deviates a bit in the right tail, but overall, it satisfies the normality assumption. For equal variance, we can plot observed error versus predictor. If variance of noise is equal for different values of predictor, it should not have pattern. In our model, noise variance is smaller for houses with big numbers of rooms. Hence, assumption of equal variance is also violated. As we mentioned before, if assumptions are violated, you cannot do statistical inference like testing and confidence interval. However, the model still can be applied to make a prediction. The accuracy and the consistency of your model do not rely on these four assumptions. Let us make a conclusion. So far, we discussed simple linear regression model and the idea of ordinary least square estimation and diagnostics of model assumptions. In the next two videos, we will use multiple linear regression models to build a prediction model for price change of SPY, which is the ETF of S&P 500, using multiple global index as predictors. Finally, we will apply our model in paper trading and evaluate the performance of our models.